Okay, so we're going to carry on with our discussion of crossing the reality gap today. Just to refresh your memory, we talked in lecture 16 about the radical envelope of noise hypothesis. So evolution is an exploiter. It will try and exploit anything that exists in the simulator, things that are physically accurate and things that are not so physically accurate. Last time we talked about the Golem Project. This was a project in 2000 when 3D printers were just starting to become a practical technology. And the idea behind the Golem Project was, let's connect our evolutionary simulation to a 3D printer, use our evolutionary simulation to automate the design of robots, and then use 3D printers to try and automate the manufacture of robots. And if not, every robot we evolve crosses the reality gap. No problem. As the years roll on and 3D printers become better and faster and cheaper, we can just keep printing out more and more of our evolved robots until one or more of them crosses the reality gap. So, a good solution, but obviously we would like to try and ensure that most of the things that we manufacture in reality reflect what happens in simulation. So today in lecture 18, we're going to talk about the Resilient Machines Project. This was a project that I was involved with when I joined Hod Lipson, who was the primary investigator of the Golem Project at Cornell. So you can think of the Resilient Machines Project as sort of part two of the Golem Project. We're going to go through the details of the Resilient Machines Project today in lecture 18. The basic idea in the Resilient Machines Project is, instead of just evolving a controller in a physics engine, let's also evolve the physics engine itself. We're going to place various parameters of the physics engine under evolutionary control. What do you think the fitness function would be? What are we going to try and evolve the simulators to do? Or what property do we want them to have? So I'm going to show you in the Resilient Machines Project, we're actually going to have two evolutionary algorithms, one that's evolving controllers for robots in a simulator, and a second one that's evolving the simulator in which the controllers are evolved. Fitness function for the controllers is going to be what it normally is. We're going to evolve robots to move as fast as possible. What would we be evolving the simulators to do, do you think? What properties do we want them to have?
Make it harder for the robot to evolve, or make it harder for the robot to get better.
Make it harder for the robot to get further. Why might we want to do that?
To kind of increase the, resiliency of the robot.
We could do that, so we could make things more difficult for the robot, so it's going to have to be resilient and adapt. That's not quite, we could do that, though it's not what we did in this project.
We could change the environment.
We could change the environment, that's right. So there's lots of things we could do to try and make the robot more resilient or more robust. I'll give you a hint. We're trying to cross the reality gap. What might you evolve about the simulator to help with the reality gap issue? Try and make it as close to reality as possible, right? Can we actually use evolution to tune up the simulator? So unlike noisifying the simulator, can evolution indirectly figure out what aspects of the simulator are incorrect and evolve them so that now we're able to move controllers better from simulation to reality? So again, we're going to go through the details of resilient machines in a moment, but just keep in the back of your mind, the basic idea here is evolve controllers and also evolve the physics engine itself. Okay. Final projects, everybody is going through the projects from last year. You're thinking about things you want to tackle. Okay. Okay, so on to lecture 18. And as you can tell from the name of this project, the Resilient Machines Project, we're going to tackle this issue of resiliency in addition to tackling the reality gap problem. So what is resiliency? Well, to try and motivate what resiliency is, I usually show these four images. The two images in the top row show how the way we manufacture things has changed over the last 120 years. And the bottom pair of images shows the ways in which we build things out of doors has changed, or not changed so much, over the last 120 years. What's the difference between the top pair of images and the bottom pair of images?
Controlled environment.
Sorry? Controlled environment, right? So you're all robotics experts by now. You know why the manufacturing revolution happened, because we created these things called factories, which are controlled environments, and they allow industrial robots, which were invented in the 70s and into the 80s, to automate the way that we build things indoors. Of course, robots would also be useful in outdoor environments. We don't really see autonomous machines yet in outdoor environments because it's very difficult to grapple with uncontrolled environments. Autonomous cars may or may not be appearing in the next few years. We may now just be getting to the point where we're starting to be able to create autonomous and adaptive machines that can work in uncontrolled environments. So what is it about uncontrolled environments that make things so difficult? Well, one of the things that's difficult about uncontrolled environments, if you're an agent trying to move about in an environment that's changing and maybe changing in unexpected ways, you need to deal with issues of robustness and resiliency. So we're going to start by distinguishing between robustness and resiliency, and I'm going to show you this robot that we built that exhibits resiliency. So robustness is the idea that you notice the environment has changed somewhat, and you decide that whatever your mode of operation is, just keep executing that mode of operation, but do it slightly faster, slightly stronger, sort of push through whatever change there is out there in the environment, and you'll still get the job done. But as the changes in the environment become deeper, there comes a point where your current way of doing things is no longer going to work. You stop. You formulate a new plan of attack and carry that out, right? That's resiliency. So the environment changes to the point where you say, there's something I need to get done. My current way of doing it no longer works. I need to come up with a new strategy. It's exceedingly difficult to create a machine that knows when to make that switch. When do you switch between robustness, just trying to power through the environment, and resiliency? Okay, and we'll connect this idea of resiliency back to the reality gap as we go. Okay, I'm going to show you three videos here that just summarize this project, and then we'll go from there into a little bit more details. So we're first going to evolve a robot, a physical robot. I'm going to have to show these videos manually. Hang on a moment. If I can. There we go. Okay. So step one of the Resiliency project is to use an evolutionary algorithm to evolve legged locomotion. We'll talk about the details of step one in a moment. So there's an evolved gait that evolution found for this robot. After the robot has evolved a particular gait, we go in and introduce an unexpected change. In this case, it's not a change to the environment, but actually it's a change to the robot's body itself. We sent in the graduate student in this project, and he mechanically separated the lower part of the robot's right leg. You can see that the motor is still actually connected to the robot, so the robot can still send commands to that motor. But now, when it tries to do what it did before, it no longer works. Okay, so here's the robot just after damage, and you can sort of see what it tries to do. So now that the robot has experienced some unexpected change, at this point the robot doesn't know what's happened, but it's going to have to diagnose what's gone wrong and then formulate a new gait to compensate for this unexpected change, right? That's the resiliency part. I used to be a 4-legged robot. This gait worked. I've now figured out that I'm only a 3.5-legged robot. That gait that worked before no longer works. I'm going to have to re-evolve a completely different gait. And so in step 3, it actually does find such a gate. And I'll play these gates a few times throughout this lecture. You'll be able to see that this gate is actually qualitatively different from the one before. Okay, so those are the three phases to the experiment. Phase 1, evolve a gate. Something in your environment or yourself changes unexpectedly, figure out what's gone wrong, and evolve a way to deal with it. Okay. That's resiliency. Let's put that now back into the context of the reality gap problem. This is just a summary of some things we've already seen. So far, we've sort of seen 3 different approaches to evolutionary robotics. In the early days, in the 90s, when simulation technology wasn't that great, they used the physical Kepera, the little wheeled robot itself, and would do evolution directly on the robot, which is fine, but obviously it has a major drawback, which is that you're going to have to do all the physical evaluation on the robot itself, which is, again, okay as long as you have a simple 2-wheeled robot. But as we scale up to robots that have hundreds or thousands of motors and sensors, there's many more things. There's many more different ways in which they could move. We're going to get into millions and maybe billions of evaluations. Just isn't practical to try out all these things directly on the physical robot. So starting around the year 2000, when these physics engines started to appear on the market, a lot of roboticists adopted physical simulation. And as we've seen many times by now, create a simulation of the robot or evolve both the body and brain of the robot in simulation. Do a lot of simulation there, and then sorry, we're talking about this. We're talking about this one here. That's right, the second one. Create a simulation of the robot, away you go. But of course, it requires someone to create the simulator itself, which you've been doing over the last 7 weeks or so, and it introduces the reality gap problem. Right? No physics engine is going to be a perfect reflection of reality. Okay. So both of these approaches have major drawbacks. A third one that we haven't really talked about but does exist in the literature is take a physical robot, try and manually design a good enough controller, something that at least generates the rudiments of the behavior you want in the physical robot. So take that hand-designed controller, give it to evolution, and allow evolution to then improve on that controller from there. This also has a major drawback, which is, of course, you need to be able to create a good enough controller in the first place. And if you remember back to lecture 5, our discussion about artificial neural networks, they're exceedingly non-intuitive and they're very hard to design by hand. Right? So these are sort of the 3 major approaches to evolutionary robotics. Each of them has a major issue that needs to be dealt with. So in the Resilient Machines project, which when you read the reading for today, it's technically called the estimation exploration algorithm. And I'll talk later about what I mean by estimation and exploration. This is a 4th approach now where we're going to evolve the simulator itself. And the fitness of a simulator is how well it allows things to be transferred from simulation to reality. Then take your evolved simulator and use that evolved simulator within which you evolve controllers for the robot. Okay. That's the 4th approach that we're going to talk about today. Okay, so I'm going to now, in the next dozen or so slides, I'm going to walk you through one long evolutionary run. This is just one run, and you're going to see these 3 phases. The phase that deals with the intact robot, what happens when the robot becomes damaged, and how does the robot recover from that damage, phase 3. Okay, so in this case, we're starting with our physical robot. We already have a physical robot in existence. This robot, however, does not have a simulation of itself. So you spent the last 7 weeks building a simulation of a quadruped. Can we automate that whole 7 weeks of work and instead start with an empty simulator and give the robot a little bit of information about itself? So in this case, in this experiment, we told the robot, you're made up of these 9 parts, but we're not going to tell you how these 9 parts are put together. So we're going to evolve simulators, and we're going to start with empty simulators and evolve them to the point where we have a simulated quadruped. Our physical robot has 8 motors, so again, this is not unlike your quadruped, right? You probably recognize this. Our robot, in this case, however, the physical robot only had 2 sensors, which were vestibular sensors. So on the main body, there was a sensor that was recording how much the main body tilted forward and back, and a second sensor which detected how much the main body tilted left and right. So every time the robot moved, there were only 2 numbers that were being recorded, which indicated the orientation of the main body. No touch sensors, no proprioceptive sensors, that's it. Okay, so we've got a robot, we give it an empty simulator, and it's going to try and evolve a simulation of its physical self. That's where we're starting. Okay, so the first thing that happens, obviously, is the physical robot needs to move. It needs to have a little bit of experience from the real world to try and start evolving a simulation to match that reality. So in this particular evolutionary run, the robot executed a short random command, which in this case rotated motors 1 and 5 down and the other 6 motors up. Remember that this robot knows that it's made up of these 9 parts, and these little gray boxes here represent that there's a motor attached to 8 of the 9 pieces. So the robot knows that it has 8 motors, it's got these 9 pieces, but it doesn't know that motor 3 is on the left side and motor 7 connects the lower leg to the upper leg in front of it, and so on. Okay, let's see if this will play in here. No. I apologize, we're going to have to do this manually today. Physical pose 3. Okay, here we go. Okay. So the robot rotates motors 1 and 5 down and the other motors up, and it records at the end of this motion 2 numbers. How much it's tilted forward and back, how much it's tilted left and right. So the robot, the physical robot, now has 1 data point. When I rotate my 8 motors in this way, I get this sensory repercussion, right? Remember our discussion about embodied cognition. An embodied agent uses its body to learn about self and the world. So our robot has only learned that fact. I move in this way, I get back these 2 sensor values. Okay. The physical robot pauses for a moment, and now I'm going to use verbal shorthand here. The robot starts up a simulator. Of course, we started up the simulator on behalf of the robot. And now the robot is going to start trying to evolve a simulation of itself. So we're going to start up now the first evolutionary algorithm. And this is the evolutionary algorithm that's going to evolve simulators. So in this case, we left the details of the simulator fixed, but it was the simulation of the robot itself in the simulator that we're going to evolve. We could place other aspects of the simulation under evolutionary control, right? We could evolve friction, we could evolve gravity, we could evolve details of the collision detection and resolution inside the physics engine. We didn't do that in this experiment. We're just going to allow the physical robot to evolve a simulation of itself. Okay. So I'm going to play this video in a moment. You can see the first random simulator or simulation that the physical robot has made, which obviously is not a very good reflection of its own body plan. When I start up this video, what you're going to see is this simulated robot here is going to play out exactly the same motor program as the physical robot did. This simulated robot is going to rotate motors 1 and 5 down, and all the other motors up. And what do you think is going to happen? It's not going to move the block at all. It may move the block, but probably not in the same way that the block or the main body rotated here, right? So when this simulated robot carries out the same motor program as the physical robot, we're also going to get back 2 numbers from the simulation. So there are 8 simulated motors over there and 8 simulated vestibular sensors. We're going to get back 2 numbers, which is how the block or the simulated main body rotating? What do you think the fitness is of any given simulated robot here? How well it matches, how well the simulated sensor values match the physical sensor values. That's the fitness function. We're going to try and minimize the difference between the sensor repercussions of the movement of the physical robot and the same movement carried out by any given simulated robot. Okay, that takes a little bit to digest, right? So we're evolving simulated robots, and we're going to allow the physical robot to create a model of self by saying, if I'm put together in this way, and I moved in that way, did I get the same sensory repercussions as I did when I moved in reality?
Why is the block in the simulation?
The block is meant to represent the main body here.
So it's as if there are two bodies in the simulation, a block and a robot.
It's hard to see. Let me start the video, and maybe this will be a little more clear. Okay. Makes sense now? So you can see the colored pieces correspond to the 4 upper legs and the 4 lower legs. So we started with a population of random simulated robots, and the fitness of each of these simulated robots is how well they match the sensor data returned by the physical robot. You'll notice that the main body is tilting up and into the screen. So my apologies on the camera work on this one. The cameras should actually be rotated 90 degrees counterclockwise. So the green block should actually be rotating to the right. Most of all of the simulated robots that you're seeing here are actually matching the physical experiences from the physical robot, right? So this is problematic. The robot says, aha, there's 10 different simulated robots. I got perfect fitness. They all match exactly the experiences of my physical self. What's the problem? You need more data, of course, right? So at this point, we have an ill-defined problem. There are lots of simulated body plans that match the physical experience of the robot. So the physical robot is now going to have to carry out another action. If you were the physical robot, what action would you carry out next?
Tilting in another direction.
Tilting in another direction, right? It probably doesn't make sense to do exactly the same thing. You already have that experience, so try and do something different. Okay, so we had the robot carry out a random action. It updated, it evolved a simulation of itself a little bit, and now it's going to carry out a second action. This is an illustration of what we just talked about. We simplified the kinds of motor programs that our physical robot can carry out. At this point, it doesn't have a neural network. We just evolved, we evolved sets of 8 numbers, which were the desired angles for the 8 motors. Here's an action here which actually caused the main body not to tilt, actually lift up off the ground. If you have an inaccurate model of self, the main body is going to tilt differently in simulation than it did in reality. You're going to get high error between the simulated sensor values and the physical sensor values. If you have the right model of self, you should get lower error. If you have enough data, right? But at this point in the experiment, we only have 1 data point. It's not enough. Okay, so what does the robot do next? It performs another action. And in this case, it tilts a little bit in another direction. So now we have another data point. We go back to the simulation. And we keep evolving. And if you watch carefully in this video, you'll see right towards the end of the video, it converges on a pretty good description of self. Right? So the basic idea here is the robot is going to alternate between performing a simple action in reality, evolving a simulation of self, going back and performing a new action, going back to the simulation, going back and forth between these two. What I'm showing you in this video here is the seventh pass through this process. So in this system here, at this point in the experiment, the robot had 7 data points. It had performed 7 physical actions and got back 7 pairs of vestibular sensor values. At the beginning of the 7th pass here, this was the robot's best idea about how it was put together. And I'm showing you this video here because, as you could see, just about halfway through this video, let's see if I can pause it here. Evolution hits on this solution, which explains most of the 7 experiences it's got so far. So suddenly fitness jumped up. This explains most of those 7 actions. And then a very short period later, it's replaced by this model. So in this video here, again, I'm just showing you one model after the other, but on the kth pass through this process, in this case k equals 7, we're on the 7th pass, each simulated robot plays back the 7 motor programs that the physical robot did, and we're matching, or we're looking at the distance between the simulated and physical sensor data between each of these 7 cases. So on the first pass through, every model during evolution is evaluated once. Second time through, every model is evaluated twice, and so on. Tyler.
How come the block is moving when it looks like the legs aren't attached to it?
Why does it look like it's moving when? So this is, again, an inaccuracy in the simulation here. I think the rotational joint is either attached here or here. It's actually in contact here, pushing down and rotating upward. So this is actually an important point, is that these simulations are obviously not perfect representations of our physical robot, right? The main body does not have this particular shape. The lower and upper legs don't exactly look like this. They're not attached at exactly the same point, but they're close enough. So far, so good? Okay, so let's continue on with this hypothetical experiment here. So at the 7th pass, the robot suddenly hit on a self-model that explained all of the 7 experiences it had had so far. I'm going to now jump ahead to the 16th pass. And this is the 16th action that the robot performs. Okay, now we have 16 data points, 16 actions, and 16 sensory results. And let's go back to the 16th pass-through simulation, and this is what's going on in evolution here. The population of models have all converged on this particular self-model, right? So instead of spending 7 weeks having a student build a simulation of our quadruped, the quadruped, by performing actions and feeding that into an initially empty simulation, automatically evolves a simulation on its own. Okay, obviously there are a lot of inaccuracies here. I mentioned a few of them. What else is different between this simulated robot and its physical self? The color's different, but that probably doesn't matter, right?
Are the masses of the physical robot in the simulation obviously different?
Absolutely, right? So the mass distribution of this robot is quite different from the physical robot. Very important, right? What else is different? Might be hard to see from this picture, but the upper and lower legs are bent a little bit, right? They're not perfectly straight. And that may just be, if we kept running evolution, maybe it would have straightened the legs. I think that they're bent actually because it's trying to reflect the mass distribution of the physical robot. The mass distribution of the physical robot is not perfectly symmetric. and we did not give the robot the ability to evolve the masses of each of these individual pieces. But by changing the geometry, the rotation of these pieces slightly, it might be able to slightly better match the mass distribution of the robot. So this is a really important point, right? Again, we're never going to have a perfect simulation. We want to have a simulation that's just good enough for us to transfer controllers from simulation to reality. How good is good enough, right? Here we have a robot we have a system where it's able to try and improve that simulation. Even if some aspects are not under evolutionary control, like mass distribution or friction, it might be able to use the other aspects of the simulation that we put under evolutionary control, in this case geometry, to compensate for those things. Okay, so that's the first evolutionary algorithm, which is evolving a simulation of the robot itself. And I need to plug in my computer here. It's not that resilient if it doesn't have power. Okay. So that's phase one. As you can probably imagine, what's going to happen now in phase two is, now that we have our evolved simulator, and here it is, you know it's evolved because you can see the legs are a little bit bent. We're going to start up our second evolutionary algorithm, with which you're all familiar with. This one is going to evolve controllers for this simulated robot. Sim optimize gate, okay. And I'm not going to show you much of the details of this second evolutionary algorithm because you've seen this many times before. Evolve a gate for this robot that gets it from the left to the right, and it came up with this particular gate. We now take that evolved controller and run it on the physical machine. I don't know if I can play these in parallel. Let's see if that works. How did we do? Crossing the reality gap. Not too bad, right? So we definitely got the robot to locomote, and it crossed the gap pretty well, even though, of course, this simulation is not a perfectly accurate representation of the physical robot. Okay, so that's a way to attack the reality gap problem, right? Let's not create our own simulation because we don't know what aspects of the physics we need to get right. Let's allow evolution to create a simulation for us. That was phase one. When we finished that, we realized, well, that's kind of cool. Now that we have that, even if we make changes to the robot and feed those changes back, it should be able to automatically update the simulation to match whatever has happened, whatever has changed in reality. So that led to this idea of adding in resilience. So let's carry on with that. So you already saw this now, but I'll just play it for you again. Now we go in and damage the robot. And again, it doesn't have any pain receptors. It doesn't know that we mechanically separated the lower leg. There's no local sensor here that says this piece is missing. All this robot knows is that I performed this simple action before, and when I performed this action before, I tilted 60 degrees to the left. Now I'm performing the exact same action, and I'm getting a different sensory result, right? The moment it detects that, it stops moving and says, okay, I can't use that gate anymore. Something has changed. Either I've changed, the environment has changed, or both has changed. So the robot pauses the second evolutionary simulation and goes back to the first evolutionary simulation where it's updating a model of self. Okay. Okay. So when it starts up the first evolutionary algorithm, at this point, this is its best conception of self. But now it had those 16 actions, and one of those actions, when it was repeated, produced a different sensory result, right? So its data set has changed. The 15 points were the same as before. Now one is different, and it turns out that this model matches those 15 actions, but not the new 16th action. So its fitness, the fitness of this one, which was high before, now drops a little bit. It explains 15 of the 16 actions. But we're going to allow evolution to continue and see if it can find a new model of self that explains all 16 actions. Okay, here we go. It actually hits on the right solution early on, but the bending of the legs was a little bit off. It thought about whether its leg had shrunk, but that doesn't make physical sense, so it doesn't end up matching the data very well, and it eventually comes back to this solution. So in this case, one other detail I forgot to mention is we expanded the evolutionary algorithm here, so now it can evolve not only which pieces are attached together, but what are the sizes of those pieces. What solution did it come up with here? Look carefully. It shrunk the blue leg a little bit, so again, it's kind of compensating maybe for mass distribution.
Just made the end of the purple leg really tiny.
That's right. So the lower leg is still there, right? It's shrunk 100 times, which again doesn't make physical sense. It's not a very accurate reflection of reality, but it's accurate in the sense that it explains all of the sensor motor experiences that the robot has so far. So it's good enough, right? Okay, so the robot says, yes, Barry.
Sorry, so broad strokes, at first the robots get a conception of self like this, and it's doing it again here because
That's right.
we've removed the leg. And then the second thing it does is evolve the controllers.
That's right.
Meaning the motors or the motor
It's
neural net.
It's evolving a neural network to control the robot. It wasn't actually a neural network in this case, but it was a controller, right? So not unlike what you're doing in your assignments. You just happen to make a simulated robot by hand. In this case, it's a physical robot making a simulation of itself automatically. We're replacing the task of building the simulation with an automated process, which is evolution in this case.
Right. And when we do this again, it understands what it is, conception of self, and then it moves that self through the...
Then it tries to move that self, right? So what I'm going to show you in a moment is now the simulation has changed, right? This is the simulation that it has. It freezes this body plan. It says, this is the simulation. Then it takes a population of controllers, takes each of those controllers, and runs it on this simulation, right? Not unlike what you're doing in the 10 assignments. That's the idea, right? We're evolving simulations. Once the robot gets a good simulation of self, evolve controllers on that evolved simulator, on that evolved simulation. Yep?
Yep.
Okay. All right, so here we go, right? So again, we just ran the first evolutionary algorithm, and again, I've compressed things here a little bit, but when it's damaged, it does the same trick. It goes back and forth between reality and simulation. If one action in its damaged state was not enough to converge on a good description of self, then it would perform a new action, get some more data, and keep going. How does the robot know whether it needs, how does the physical robot know whether it needs to perform more actions to improve the simulations? Remember that it has no direct knowledge of its physical self, so how does it know that the simulated self is a good reflection of reality? How does it know when to stop going back and forth alternating between reality and evolving a simulation of self? There's more than one solution, right? If there's more than one solution that's explaining all of the data that the robot has so far, the robot at least knows, quote unquote, that it can't have multiple forms, right? It has only one physical form. So if there's lots of different physical forms that explain all the data, it needs more data. So it keeps doing this until the models all converge to one description, right? They all converge to the same thing. That's probably a good signal that you've now got a good description of self. So far, so good? Okay, so back to this one evolutionary run. We now have our damaged physical robot. This is its best conception of self. So now we go back to we go back to the second evolutionary algorithm, which is evolving controllers on the evolved simulator. But the simulator is now a 3.5-legged robot, not a 4-legged robot. And that evolved gait that I showed you before for the intact robot, if you rerun it on the 3.5-legged robot, doesn't work. The robot doesn't travel from left to right anymore. So the fitness of that gait, or the controller that produced that gait, drops. But evolution doesn't care. It just keeps going. And it evolves a completely new gait, which is this one here. You're all experts on physical simulation now. You can probably guess that these motors are way too strong. There's something else that's problematic with this gate. What is it? It's going in a circle, right? Now, of course, we fixed the number of time steps that we evaluated each controller, so it doesn't care, right? We didn't say anything about and don't travel in a circle. So we're back to the Ministry of Silly Walks problem, right? If we were to do this again, we'd probably evolve for displacement and evolve for as straight travel as possible. That wasn't the goal here, so we just left it as is. Okay, so now, again, the robot says, I become damaged. I know how I'm damaged, but now I'm resilient. I've come up with a qualitatively different gait that allows me to fulfill the utility function that I've been given, which is travel from left to right. Okay. Obviously, the physical motors are much weaker than the simulator motors, but seem to be okay. Not very efficient, but at least getting there. Okay, so I've just walked you through one evolutionary run, and of course we picked this run because it was successful. It wasn't always successful. But the basic idea, carry out actions in reality, get new information, use that to evolve a simulation of self. From time to time, perform actions that you've performed in the past. If those actions give you back a significantly different sensory repercussion, stop. Update model of self, use the new model of self to come up with a new action that fulfills the utility function, which in this case is to get from the left side of the table to the right side of the table, and continue. Okay. Any questions about the basic process here? Yes?
If you were to replace the leg, would it forget its old gait?
If you were to replace it, it depends. So if you put the leg back on, if you fixed it, and it would then say, oh, wait a second, my experiences have changed again, it would pause the second evolutionary algorithm, go back to the first one. It depends. This gait, who knows, it may actually work for a 4-legged robot. The fact that it's turning in a semicircle makes me think that probably it wouldn't. It would probably head off in another direction.
But does it remember the previous gait? So if it was more efficient, would it have to evolve again?
Good question. It does not remember because we're just using our evolutionary algorithm. So the gait for the intact robot got low fitness and was bred out of the population. It won't remember. So if we went back, we would probably get a different gait. Okay, let's pause here for a moment and talk actually about gait. When we originally did this experiment, we built it as a 4-legged robot, assuming that it would stand up and exhibit one of the canonical quadrupedal gaits. It didn't. You get this funny inchworm type locomotion. We ran it again with a different initial population. It found this solution again and again and again. Never found upright legged locomotion. Why not? Recall our discussion about legged locomotion. What's the advantage of upright legged locomotion over peristaltic or inchworm type locomotion?
Mostly efficiency.
Efficiency in which sense? Energy efficiency,
Yeah,
right?
like it's a lot less robust because you can fall over, like you need to devote a ton to balance and whatnot. But if you're lying on the ground, the there's not really anywhere to fall to,
Exactly, right? So you're much more stable on the ground. So think about the rudiments of this peristaltic motion, right? Maybe early in the evolutionary run, it got a couple of oscillations and then stopped. If you then took that controller, copied it, and introduced a mutation, it might travel a little bit further or maybe slightly not as far, right? Mutations are going to have a slight impact on the gait, which is good news for evolution, right? Evolution wants to make lots of these baby steps. If in the same population there was the beginning of upright legged locomotion, so maybe there's a controller that actually did get the robot to stand up and take one step and then fall over, very hard to imagine a subsequent mutation that's going to allow it to still take that one step and not fall over and take a second step. That's much less likely. So the worm controllers are probably outcompeted any rudiments of legged controllers that were appearing in the population. We didn't go back to see if that was actually the case, but I would bet you that that's what happened. Right? So a good reminder about evolutionary robotics is it might give you a solution that works, but not in the way that you expect it to, right? And those of you that are running your assignment 10s, you're probably seeing a lot of that now. Okay. Okay, so that was a typical experiment. I apologize about the pictures down here that didn't turn out very well. This is just an image to try and summarize what I just showed you. Up here, the robot is evolving conceptions of self. So the question marks is basically the robot saying, which of these, if any, is my true state? The robot then thinks about what action to perform next, carries it out on the physical robot, and goes back and forth between carrying out actions in reality and thinking about them, alternating back and forth here, until eventually it converges on a correct model of self. Then goes to this phase here where it evolves controllers on the evolved simulator, and then tries out those evolved controllers in reality. If at some point something goes wrong, something changes, it goes back to this cycle. Once it reconverges on an accurate description of self, it re-evolves a new way of moving, and around we go. Okay, so back to the technical term of this the technical term for this method. The robot is estimating a sense of self, so it's trying to estimate or model itself. Exploration over here means how should I move next to get some new information from the real world. And as we've talked about so far, a good way to explore is to do something as different from what you've done before, right? Don't perform the same action, explore. Try something different, which will give you new information, which will help you better estimate self. What's missing from the title here is the third stage, which is exploitation. Once you have a model of self, exploit it to do whatever you want to do. These self models are useful for not only robots, but also organisms. So a famous scientist from years back, Karl Popper, said, one of the nice things about self-awareness is it allows your hypotheses to die in your stead. What did Popper mean by that? Anybody heard that expression before? If you don't have a conception of self, you can't allow your hypotheses to die in your stead, which is not a good situation.
You can think through like your actions before you do it.
Right.
They're taking an action and then dying because it doesn't work.
Exactly, right? So the robot is actually moving around on a table. We didn't simulate it, but we could have allowed the robot to simulate the edge of the table. And it would say, this is a great gate, but it's actually going to take me to the edge of the table and over the edge of the table, right? Our distant ancestors probably thought, hey, this thing looks like the edge of a cliff. I wonder what would happen if I went to the edge of the cliff and looked over, right? You need to be able to think what would happen if I walked to the edge of the cliff, right? You may not be consciously aware of that mental process, but that mental process, which you see in a very rudimentary form here in this robot, has extreme adaptive value, right? You can try out hypotheses and allow them, and the robot can allow its hypotheses to die in its stead, rather than trying out everything in reality. This was work that we did at Cornell and it was funded by NASA at the time. So NASA, one of the things that keeps NASA engineers awake at night is what happens if they get one of their robot probes to a distant planet or moon in the solar system and something really serious happens, like the snapping off of one of the robot's legs or a wheel. Imagine even worse than that, that damage occurs, but we don't have good telemetry from the robot. So back in Houston, they can't see through their various cameras and sensors that that's what's happened. If the human engineers back on Earth can at least know what's happened, they can program a patch and upload it to the robot. What happens if they know that something serious has happened, but they don't know what the problem is? Now you get into what NASA calls methods of last resort, right? That you're in danger of losing this mission, millions, maybe billions of taxpayer dollars about to go up in smoke. At this point, NASA engineers might consider ceding some autonomy to the robot. Okay, robot, you figure out what's gone wrong and try and come up with some compensating action so you can at least continue on with your mission, maybe at a reduced level of functionality, but better than nothing. Right?
That's what happened to Spirit, where it lost a wheel.
It had a problem with one of its wheels, and Opportunity also had an unexpected problem in transit from Earth to Mars. This happens all the time with the probes. Most of the cases so far, the human engineers have been able to remotely diagnose what the problem is and write a patch and upload it to the rover. But what they're really worried about is they don't know enough about what the problem is to be able to write a patch manually, right? So far, knock on wood, that hasn't happened. A version of this might be used if something like that ever does occur, right? So obviously a very real engineering usefulness and useful from an adaptive machines point of view, right? I want to be able to update a conception of self and use it to try out potentially dangerous actions before trying them in reality. Okay, so just to again use this to build up our intuition about evolutionary algorithms. Remember our discussions about genotype to phenotype. So in this evolutionary algorithm here, the phenotype, the thing that's being evolved, is the body. How are the 9 pieces put together? What are the sizes? What are the volumes of those 9 pieces? And the fitness is the similarity between the sensory repercussions of that simulation and the physical robot. Down here, I described this second evolutionary algorithm for you, which is a little bit more familiar. The phenotype in this case is the controller. We're not evolving the body now because we did it over here. We're just evolving the controller on the evolved simulator, and the fitness is, again, very familiar, forward displacement from the point of view of the robot. Makes sense, right? Okay. I'm going to come back to, I think we have time today, I'm going to come back to this part in a moment. But before I do, let's see how this algorithm does in general, right? I walked you through one evolutionary run that was successful. How does it tend to do in general? Okay. What I just showed you was one run. We actually did 30 replicates of that experiment. So we went back to the beginning. We started with the empty simulator and ran through the whole thing again. In these 30 runs, we only did part 1, which was when we had the intact robot, right? So we start from an empty simulation. We give the robot 16 actions. So the robot is able to go back and forth between simulation and reality 16 times. At the end of the 16th trial, we look to see how close was the evolved simulation to reality, right? So the outlines that you see here, the empty boxes, shows you what the robot actually looks like. And the solid shows you what the evolved simulation actually looks like. So replicate 1 was the one that I just showed you all the videos from. And you can see that it was pretty close, but some of the legs were a little bit bent. Replicate 2, it also came up with a pretty good description. Same with 3, 4, 5, 6, not so good. 7, not so good. So it didn't always work, but most of the time, at least in 13 out of the 30 runs, it got the right topology. By topology, I mean it knows which piece is attached to which other piece. Might not have the angle quite right, but it's got the topology right. Presumably, if we had given the robot more than 16, given it a budget of more than 16 actions, more of these 30 would have been correct. We wanted to just sort of see how well it could do with a limited budget. Okay. I tried to analyze the simulated evolved gait for the intact robot, the one that I showed you, versus how it actually carries out in reality. And it turns out that this gait, for some reason, transferred very well from simulation to reality, although there were particular points in the gait cycle where the robot was doing something very different. So if you try and mentally animate these images, here the robot is reared up on its back leg. It pushes with its back leg, and it starts to rotate forward, and the robot falls forward. In simulation, that kick from the back leg did not cause the robot to tilt forward. So there's a pretty big difference at this point in the gait cycle, but it didn't matter. It kept going on with what it was doing, and the simulation would eventually catch up with reality, and it works. Right? So again, this is good news in terms of the reality gap problem. We don't need to have a perfect simulation in order to be able to cross the reality gap. Okay. This picture shows you of those 30 runs that we did those 30 runs, which gave us 30 different simulations of self. We took those 30 different simulations of self, and we evolved a controller for forward locomotion on each of those 30 simulations. So 30 simulations, evolve controllers on them, take the best controller from each of those 30 runs, which gives us 30 evolved controllers. And we're going to play those back in a moment. What we then did, before we played back those 30 evolved controllers, we took the physical robot, we put it at 0, 0 on the table. So it was moving across this table. And we then tried out 30 random controllers. We took a random controller, we put it on the physical robot moved for I think about 3 or 4 seconds. We stopped the controller, and then the grad student came out and drew with a Sharpie a red dot on the table where the robot had ended up. And that's what those 30 dots represent. You can see that either the robot is a little bit asymmetric or the table was tilted a little bit to the point where on average the robot would end up a little bit forward. So I'm sorry again with the rotations here. This is the left side of the table, and here's the right side of the table. The robot would move a little bit towards the right side of the table and a little bit towards the front of the table. So random controllers aren't going to get the robot very far on average from its starting point. We then took those 30 evolved controllers that we evolved on the 30 evolved simulators. We played them on the simulated robot, and we measured in the simulation what was the final position of the robot. And we took that final position and marked it with a black Sharpie on the top of the physical table. So each of these black dots is a prediction from the simulator about where the physical robot is going to end up. So far, so good. As you would expect, most of them are falling to the right-hand side of the table. We took each of those evolved controllers, which we just ran on the simulated robot, and now ran it on the physical robot for 3 seconds. And wherever the physical robot ended up, using that evolved controller, we took a blue Sharpie and drew a blue dot at that point. I've circled 2 dots here. This is the controller that was evolved using replicate 1, so that simulated robot you've already seen. It predicted that the robot would get 45 centimeters along the table, and the physical robot only got about half that distance, 0.25 centimeters along the table. So the prediction was a fair bit off, but at least it was in the right direction, right? The robot actually did move in reality in the direction we wanted it to move. What do these results tell you about our ability, or the robot's ability, to cross the reality gap in this case? How good is its conception of self on average? Pretty bad, right? So most of the time, the simulation is overly optimistic or maybe wildly optimistic, right? The physical robot doesn't travel as far. There were a few experiments that really failed, right? It predicted the robot would move to the right side of the table, and the physical robot actually moved to the left side of the table. It went in exactly the wrong direction. Right? So not great, but at least a good start, right? We're automating this process. We could do it over and over again. We could put more aspects of the simulation under evolutionary control, which would hopefully allow the robot to produce better simulations of self and more accurate transferals from simulation to reality. Okay, so good start. So far, so good? Okay. So we've got about 15 minutes left, and so I'm going to spend the last 15 minutes here talking more about the exploration part of this algorithm. This is a little bit more involved, so this is just going to be optional. It won't show up on the quiz, but interesting to think about. If you watch this robot in action, so you watch the physical robot and you don't have any access to the simulation, what you see is the robot sitting there, and from time to time it moves, then moves in a different way, a different way, a different way, and a different way. It looks like the robot is just kind of trying random actions. If you've ever watched a baby in action, it looks like it's kind of doing the same thing, right? It's moving at random, grabbing anything that's within grasp and trying to, within reach, and put it in its mouth. This is called, in developmental psychology, this is called motor babbling. So unlike verbal babbling, it's the idea that a young child or an infant is exploring all the different ways that it can move, and perhaps, again, we don't know, it's doing something similar to what our resilient machine does here. It's collecting information, right? Whenever I move like this, I tend to get this sensory repercussion. If you're a young child and you're eventually going to have to get along in the real world, better to get as much diverse experience as you can. There's an open question in developmental psychology about whether these actions are actually random, right? So as we talked about a few minutes ago, what should the robot do when it performs a new action? Maybe it should do something random or is different from what it did before. Turns out that in theory, there's something that you can do that's better than doing things at random or just trying to do something as different from what you've done before. And I'm going to explain that to you now, and that's actually what the robot is doing. In those 16 trials, or those 16 actions, the first action was random, but the second through the 16th action were definitely not random. Okay, so in order to explain this, we're going to step back from robotics for a moment, and we're going to talk a little bit about machine learning. So I'm going to start with a very simple example here, and then we'll connect this back to the robot in a moment. Let's imagine that we're going to do a little bit of machine learning, and we want to produce a model of a physical phenomenon. In the case of our robot, it is also trying to create a model, an accurate model of a physical phenomenon, in this case a physical thing, which is itself. Right? But let's talk about the general process by which we try and create models that reflect some physical phenomenon that we're interested in. Let's come up with a very simple example here. Let's imagine we have a coordinate frame here, x and y. Let's imagine that there's some physical phenomenon that we can represent in the simple case with a straight line that passes through the origin. I'm drawing it as a dotted line to make it clear that we don't know what that physical phenomenon is. There are quantum effects. For a long, long time, we didn't know that they existed. They were there, we didn't know. Can we create a model? Can we start to figure out what this thing is? I'm going to call this, for shorthand, just the target. This is the thing that we're trying to reflect in a model. Connecting this back to our robot, in this case, the physical robot is the target. But the physical robot doesn't know what it looks like, right? It doesn't know itself. It's going to try and create a model that reflects this target. Okay, so what can we do if there's some mysterious physical phenomenon out there, or there's some target we want to model? Well, we're going to generally define some constraints of this system. We're going to say that y is equal to mx. We know that whatever this target is, We know that it's a straight line, and we know that it passes through the origin, so there's no y-intercept here. We just don't know what m is. We don't know what the slope of this target is. In a similar way, our physical robot knows that it's made up of 9 parts, or maybe 9 or fewer parts. So it knows something about the target that it's going to try and model, but there's other aspects of this target that are unknown. So far, so good? Okay, so how are we going to figure out m here? Well, we can perform an experiment, or multiple experiments. So in this simple case here, an experiment corresponds to us picking a value of x and picking a value of y. And then we conduct that experiment. We expose that experiment to our target system, and we get a response, right? There's a result of this experiment. Let's assume, again, in this very simple case, that if any experiment lies below the line, this experiment becomes a circle. For any experiment that we conduct that happens to fall above the line, the result of this experiment is an x. So let's assume that results of our experiments are just binary. Either we get back a 1 or a 0. Right? So far, so good? Okay. So how do we actually figure out what the target system is? We can't see it directly, but we can perform these indirect experiments and get results back of these experiments. What's the equivalent of an experiment over here? Each movement, right? So here's our target system. The robot doesn't know what this target system is yet, but it can perform an experiment by performing an action, which corresponds to the position of each of these points. And whenever it performs an action, it gets back some sensory repercussion, which for us is the result of our experiment, either circle or X. Slade.
So just initially do random movements. And so if you keep getting circles, keep doing that until you get an X. And then once you have both types of movement, just establish going closer and closer from one to the other until you get rapid reversal because you'd be right along the line.
That's very close to what we're going to do, right? So you start with random experiments. So since I've already drawn this, let's imagine that these are our 2 experiments we've performed so far. But we still need the modeling piece, right? We haven't introduced any models to our system over here. So we do know that the target is y equals mx. And we know that any points that fall below the line are circles. Any points that fall above the line are x's. So let's also now create some models that have different values for m. Here's one model. And here's another model. What is the fitness or what is the accuracy of these 2 models? They have different slopes, different values of m.
Some squares.
It's not sum of squares, right? We don't care how far the points are from these lines. We take each one of our models and say, okay, this point fell below this model, and it gets a circle. And this point also lies above this model, and it got an X. So this particular model here is doing perfectly, right? It is correctly predicting the actual outcomes of both experiments so far. This is not unlike when I started to show you the videos from this experiment where the robot was creating all these different self-models, right? All these different models, and all of them were explaining the one action that had been performed so far. Make sense so far? So this model is doing a perfectly good job of explaining all the observations we have so far. How about this model? Also, right? It's explaining both experiments perfectly fine. How many models actually exist? How many models could I draw on the board here that would explain both experiments? An infinite number, right? So again, we know we haven't explained our target system well because there's lots of different models that explain all the information we have so far, right? So not unlike the robot. Let's say we pick these at random, but now we're going to actually use the models, not the points, to try and think of what try and think up what experiment to perform next. We've got 2 models so far. I'm going to add 2 more just for fun, but of course there's an infinite number. Now I have 4 models. All 4 of these models explain all my observations. I drew 4 because in this cartoon here, this robot also has 4 models. We're going to try and use these models to decide what experiment to perform next. Where should I draw the next point? Which value of x and y should I pick? What about here? Is that a good model? Is that a good experiment?
Pick right in between, in the middle of all your models.
I want to pick a point that is in the middle of all my models, so I'll just put question mark here. Why in the middle?
It'll reduce it by half because it'll either be an X or a circle, and if it's an X, then all the top models are wrong, and if it's a circle, then all the bottom models are wrong.
Exactly, right? So the computer scientists in the room should recognize this. This is kind of looking like binary search, right? We're trying to narrow in. Let's think about exactly how we picked this value. It's easy because I've given you a simple example here, right? You can visually see a point that lies in the middle of these models. And as Tyler just mentioned, by picking this, what we're really doing is inducing a maximum in the variance of the predictions of the models. There's a little bit of a mouthful. Let's think about this, right? So if I do pick this point here, let's take our 4 models and get them to predict. For this point here, how do these 2 models predict? What do they predict the outcome of this experiment is going to be? An X, because this point lies above these 2 models, right? Anything that's above a line gets an X. What do these 2 models predict? A circle. So 2 models are predicting an X, and the other 2 models are predicting a 0. They disagree in their predictions. And in this simple case, that's the best we can do. We could pick this point here. There would still be a disagreement in predictions. This model would predict an X. These 3 models would predict a 0. But what we're looking to try and do is maximize the amount of disagreement, which you can think of as maximizing the variance in the predictions. For the mathematicians here, maximize the entropy in the predictions of the models. Okay, so easy, it's trivial, right? Because you can see what that point should be. It's not trivial for the robot. So now let's go to this exploration point here. Let's imagine that at this point in the experiment, this robot has these 4 models, and the robot formulates a new experiment at random. And as was mentioned, our experiment is an action. So the little green arrows here represent action. The robot moves. We take that action and we supply it to each of the 4 models, and we look at what the predictions of the models are. What are the predictions of the 4 models here? They're actually visualized over here. So this cartoon here is showing you take one action, drop it into each of the 4 models, and what happens?
2 are going to break. 2, if it's in the middle, 2 are going to break it into 1.
So here I've set it up as a binary problem, right? It breaks the prediction or not. We're not looking to break the prediction, we're looking to get different predictions from the models. So if you look carefully here with these arrows, what in essence it's doing is saying, okay, for this potential action, which you haven't carried out on the physical robot yet, this model says, I think you're going to tilt to the left. And this model says, no, you're going to tilt to the right. This model says, you're both wrong. We're going to tilt forward. This model says, you're all wrong. You're going to tilt back. Right? So the predictions here is what is the sensory repercussion of a given action. So let's say we have that action which is inducing a disagreement in the predictions of the models. We take another potential action. We haven't even carried it out on the physical robot yet. We take that action, we supply it to our 4 models, and all 4 models are in agreement. They all say the robot's going to tilt to the left. Which of those 2 actions are you going to send to the physical robot? The first one, right? Obviously, all 4 models are predicting different sensory repercussions. They can't all be right. In the same way that if we actually conduct this experiment here, we can't get back a circle and an X. It's going to be one or the other, right? So we're looking for an action that when supplied to all of the models maximizes the disagreement in the prediction of the models, and that's the action that the robot carries out next. You found the next action or the next experiment in the simple case over here through visual inspection. Our robot can't do that. What do you think our robot does? I'll give you a very strong hint. It evolves models of self. It evolves controllers. What do you think it does up here? It evolves the next action to perform, right? So in this third evolutionary algorithm, it's evolving candidate actions, and the fitness of any one action is what in this case? How different the predictions of all the models are, right? That action, when supplied to all the models, gets the models to say, we're going to tilt this way. No, 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 we're going to tilt this way, right? You're evolving actions that maximize the variance in the predictions of the models. Run this for 20 generations, whatever action you found by that point, send it to the physical robot. So one of the other things about this experiment that was interesting to developmental psychologists is it suggests that what babies are doing, or you do when you're learning a new instrument or a new sport, is not trying things out at random, but you actually have more than one model up here about what the repercussion of your new action is going to be, and you're picking what to do next based on disagreement among the models that you're holding up here. Whether that's what we're actually doing, who knows? That's what the robot does. Okay, we ran a little bit over. Thanks for your attention. We will talk about transferability on Tuesday. You have a quiz due tonight, and you have to submit your idea for your final project by Monday night, and we'll see you on Tuesday. Thank you.